Okay, Chapter 11, Section 3, the integral test and estimates of sums. Okay, so in general, it is difficult to find the exact sum of a series. We were able to do so in this previous section for cases that fit geometric series, right? Remember, just to refresh your memory, we just finished going over this section where something that fits a geometric series looked like this. A geometric series was something that fit the form of a r to the n minus 1 power as n ranges from 1 to infinity, right? And so this was something that was, something like this. A plus some constant a times r plus some constant ar squared plus some constant ar to the third power plus dot, 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 right? We keep going like that. So forever. We want to figure out the sum of all of these forever. It could be, for example, something like we want to find the sum as n goes from 1 to infinity, and it could be something as simple as 3 times 1/2 to the power of n minus 1. Right, so if we expanded all these out, this would turn out to be a 3 plus 3 over 2, 3 times 1/2, plus 3 times 1/2 squared, 2 squared, plus 3 over 2 to the third power, plus dot, 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 dot. Right, so this is a geometric series. And we were able to show in the previous section that this infinite sum in some cases will just add up to some constant, right? And we know that it will add up to some constant as long as the r value, the absolute value of r, is less than 1. So converges, I'll put here, converges for absolute value of r less than 1. And what does it converge to? This infinite sum turns into a divided by 1 minus r. Right, so in this little example, this infinite sum would be equal to 3 over 1 minus 1/2. Right, and that's because in my little example here, the r value, the constant multiple, is this half. R equals to 1/2, which is less than 1. Right, the absolute value of that is less than 1. So it converges. It converges, and it converges to this amount. Okay, so that works out great for geometric series, but what about things that don't fit a geometric series form? There's plenty of stuff that doesn't fit that form. Well, some of them have a simple formula for the partial sum s sub n, and we can figure it out from there, but many of them do not, right? So here we're going to focus on cases where it doesn't quite fit that form, but we might still be able to apply this new idea, the integral test, to be able to at least confirm that the series converges, or at least confirm that the series diverges. And also, we'd be able to get a pretty good estimate, even if not the exact answer, a very nice estimate for what that series converges to. Okay, so moving on. Let's consider this case right here. So let's say we begin by using the investigation of series whose terms are reciprocals of the squares of positive integers. So we have 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, so on and so forth, dot, 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 on forever. Notice that this is not exactly a geometric, right? A geometric would mean that from one term to the next, we always multiply by the same amount, and that's not quite the case here. From here to here, if we wanted to simplify this, let's just simplify. This is just 1, right? 1 over 1 squared, plus, and this is 1/4, plus, and this is 1/9, and then plus, this is 1/16. Okay, so when I go from one term to the next, from here to here, what do I multiply 1 by to get to a 1/4? Well, obviously, that one's easy. That's just going to be 1/4. So from here to here, I multiply by 1/4. Okay, but what about from here to here? Well, I don't multiply by 1/4. That would be 1/16. So it's not 1/4. Good. It would have to be 4/9, right? We multiply by 4/9, and that's how the 4 and the 4 cancel. We end up with 1/9. Okay, and then from here to here, we'd multiply, from here to here, we'd multiply by 9/16. Okay, so they're different, right? So whatever we're multiplying by from one term to the next, it's not a constant value r, so this is not geometric. Not a geometric series. So therefore, the properties that we learned before, the a over 1 minus r, do not apply here. It's a very common mistake people make. That's for a geometric series. What does this converge to? Well, that's what we're about to investigate. Does it converge? Does it diverge? Do we have a way of knowing exactly what it converges to? Or can we at least come up with an estimate of some kind, right? That's what we're trying to do. All right, so let's begin by investigating this a little bit more. Just go ahead and erase this. Well, like I did a second ago, let's just simplify these a little bit. So this is 1 over 1, just 1, plus 1/4 plus 1/9 plus 1 over 16 plus 1 over 25 plus ... Okay, so if we look at the partial sums and begin to build these up, okay, so s sub 1 is just going to be 1. S sub 2 is going to be 1 plus 1/4, which equals to 1.25. S sub 3 equals to 1 plus 1/4 plus 1/9. Okay, it's getting a little ugly. Common denominator, 3, 9. All right, let's just get our calculator out. So 1.25 plus 1 divided by 9. Okay, so this is 1.3611. Something like that. Okay. S sub 4. Okay, well that's going to be 1 plus 1/4 plus 1/9 plus 1 over 16. Okay, and again, I'm just going to use technology. So that was really the previous one, the 1.316. And then we add to it. So the previous result plus 1 divided by 16. 1 divided by 16. Should get us to the next one, which is 142.36. 4236. 1.4236111. Let's do one last one. S sub 5 is 1 plus 1/4 plus 1/9 plus 1 over 16 plus 1 over 25. Okay, and so the first 4 of them add up to this, so then we just got to add 1 over 25 to that. So again, let's go to our calculator and say it's the previous result plus parentheses 1 divided by 25, close parentheses, enter, and we get 1.4636. 1.463611. Okay, and so we can continue in this way, but again, we're just going to use technology to expand this out and create a table using technology to find some of these S sub n values. So here it is. Here is a table. Notice that when n equals to 5, this guy right here, this represents the S sub 5 case, n equals to 5. And well, then there's S equals to 6, 7, 8, 9. Okay, so the table skips on to S sub 10 and S sub, so the sum of the first 5, sum of the first 10, sum of the first 50, so on and so forth. So this is the one I just found up here. And if we keep going and add the first 10 of them, they'll add up to this. And if we keep going and add the first 50, they'll add up to that. And if we keep going and add the first 100, they add up to that, and so on and so forth, right? So there's no simple formula for S sub n, the sum of the first n terms, but the computer-generated table of approximate values gives us, given in the margin, suggests that the partial sums are approaching the number 1.64 as n goes to infinity, right? So it looks like they're starting to get really close to 1.64444, right? And that's just based on using technology to create this table and seeing that the sum of the first 50,000 go to here. And if we can use computers, you know, we'd find the sum of the first 10,000 of these numbers, and we'd see that it's getting closer and closer and closer and closer to 1.64-ish, right? It looks like we're getting really close to that. Okay, we can confirm this impression with a geometric argument using the figure below. Okay, remember that we're working with this formula right here. Sum of 1 over, we're working with this series here, the sum of 1 over n squared as n goes from 1 to infinity. So this is representing this sum, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus dot, 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 dot. Okay, but there is a relationship between this and this function, f of x equals to 1 over x squared, right? When we see this, when you see 1 over n squared, this is for cases where n equals these counting numbers, right? N equals 1 and 2 and 3 and 4, dot, 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 dot. Remember that these go back to referencing the location on the list. The first one on the list, the second one on the list, the third one on the list. This is a formula that can generate the value based on the location on your list, right? If I want to know the 7th one on the list, I let n equal to 7, and I know that 1 over 49 is the 7th value in this series. Okay, well, in contrast to that, when we have something like this, this is for x being a real number. This is a function where the domain is usually by default identified as the set of real numbers. Now, it might be positive real numbers exclusively, or it might be positives greater than 1, for example. So this this function is often used to compare these two, where this is a function with domain x strictly greater than or equal to 1, right? Where x is a real number. X is an element of the real numbers, right? It's a real number. So it could be a decimal, it could be a fraction, it could be any number that's strictly greater than 1. So when we graph these things, let's go to Desmos. What are we talking about? Let's go to Desmos. So if I have my function f of x equals 1 divided by x to the power of 2, divided by x to the power of 2, it looks like that. Let's make it blue. That. Done. Okay, so we're going to focus on the case where x is greater than 1, like this. So here is the function. X is allowed to be any one of those values on there, right? So x could be the ordered pair. Okay, so here is the function f of x equals to 1 over x squared. And if I let this little guy here be a slider, it'll show you the value as we move it along, right? As we move this along, we get different values, right? But it could be anything. Okay, by contrast, if we're looking at the series 1 over n, so this is this guy, that's going to be n, and this guy is 1 divided by n, to the second power like that. And so it becomes 1. And let's make this a different color. Say green. Okay, so it's 1, and then this is 2, and then 3, and 4, and 5, and 6, and 7. Okay, so the individual green values, little green dots, is the series, right? So just those green dots right there become the series, which of course it's related to the function f of x, right? Because all the green dots are a value on the function f of x, but it's not every single value, right? So not every single value of the function. It's just the ones that happen to be integer values, greater than 1 in the domain of f of x are the values that end up being in the series that we're working with, right? Just those individual ones. Okay, so what we're going to do is we're going to think of a couple of things here. So let me get a picture of this. What we're going to do is think about the following thing. We want to find the sum of all of these green dots. And what we're going to do is we're going to think about looking at a square that has a height of up to there and then comes away to the left like that. And so I'll have this square here where the base is definitely a 1 and the height is equal to the value on that other function, right? I also want to come over here and do it here. Now I know I cut it off, but I want to go this way like this. And then this is also going to be a 1. And the base is 1, and the height is equal to the value of the function. So remember that this is 1 over n squared. So when n equals to 1, this is just going to be 1, a height of 1. And then here, this is a 2, so this is going to be a height of 1/4. And then over here, this is coming like so, like that. We're going to create this box right there. And the height of this guy is going to be 1/9. The height of this one is going to be 1/16. And again, we're going to create this little box like that, where this is definitely always a base width of 1. The interesting thing about considering these rectangles where the base is a width of 1 is that then 1 times any number is equal to that value. So therefore, all the areas, right, and if we convert it and think about the area of each one of these rectangles, the area is going to be equal to that same value. 1 times 1 equals to 1. So the area of this one is a 1, right? And the area of this one is going to be 1/4, because 1 times a fourth is a fourth. And the area of this black one, this little rectangle here, is equal to 1/9. And then this one is going to be 1/16, right? Because its width is 1. And then so on and so forth, so on and so forth. Keep going. I know it's, it becomes difficult to draw it, but we just keep going on that way forever. So what we've done is we've turned the idea of adding the 1 plus the 1/4 plus the 1/9 plus the 1/16 into the idea of finding the area of all of these rectangles and adding them all up together. Now that problem, you're like, what's the problem? That's just as difficult as the original one, right? So basically I've turned this question, what's 1 plus 1/4 plus 1/9 plus 1/16 plus ... forever, this, and I've turned it into areas. Area of this first one, okay, that's going to be a 1, the area questions, area. Plus then the area of this one, well, that's also 1/4, okay, the area is 1/4. Plus the area of this one, okay, what's also 1/9, okay, and then the area of that one, okay, well, 1/16. So they look exactly the same. What's the difference? How does this help anything? Okay, So what we want to do is, now that we've converted our question of adding a bunch of fractions into a question of finding the area of a bunch of rectangles, now what we want to do is think about comparing the area of all those rectangles and comparing it to the area of the function f of x below the function f of x and below the function f of x and above the horizontal line, above the horizontal axis, but below the function 1 over x squared. Let me repeat that again. Now that we've converted the question of adding a bunch of fractions into the question of, let's find the sum of all the areas of all these rectangles, now that we've converted that, at least mentally converted that, the advantage of that is that now that we're thinking about areas, we can compare the sum of the area of all these rectangles to the area that is below the function 1 over x squared but above the x-axis, right? So what we want to do is compare the sum of all those black rectangles to, let's put it over here, compare all of those to the area underneath the curvature starting at 1 forward this whole area here. Right, that's what we want to accomplish. Well, that brings us then to the integral territory, right? That's what integrals do for us. They tell us the area of the function trapped between, between the function and the x-axis. Good. So this area in red, this area is equal to an integral of 1 over x squared dx, and we're starting at 1 and heading out forever. So we're looking at that, right? So we want to, this is an integral, hopefully, that we are able to integrate. And then that can serve as a very good comparison for what we wanted to find, which is the area of all these little rectangles over here. Okay, so your author provided some really nice graphs to this, so let's see what they have. Okay, so here we go. Here is the function 1 over x squared. That's this function here. Oops. That's this function right here. And then we've converted the infinite sum of fractions into the infinite sum of all these areas, area of each one of these little blue rectangles. Okay. Notice that the way we've drawn it, right, in this case, the way we've drawn it is that we take, when n equals to 1, the very first one in my list, right, my list starts with 1, then 1/4, then 1/9, and so on and so forth. Okay, the very first one in my list is right there, and I go to the left and go down. I maintain the f of x function above. Good. And then the very next value on my list is going to be 1/4. So now I go to the left and create this rectangle. And again, we're beneath the curvature. Good, beneath the graph. Okay. Keep that in mind. Okay, so the base of each rectangle of the interval is length 1. The height is equal to the value of the function. And we have a right endpoint for the interval, right? So we're using this. The right side of the rectangle goes up to the function, which means that all the rectangles are below the function f of x. That's important. Okay, so the sum of areas So the sum of the areas of the rectangles, this, which equals to this, right? So this is area 1, rectangle 1, area 2, area 3, so on and so forth. That infinite sum, which is equal to what we're interested in, the sum of the series. If we exclude the first rectangle, the total area of the remaining rectangles is smaller than the area under the curvature y equals to 1 over x squared, for x being greater than or equal to 1. which is the value of this integral, right? What's that saying? Let's go back up here. All right, well, this is just going to shoot off toward infinity. Remember that if we look at our Desmos graph, right, this shoots off to infinity, right, as the function approaches 0. So we want to avoid that. But instead, what we're going to do is just think about the integral from 1 to infinity underneath the blue function, right? That's something hopefully we can do. And now if we simply kind of take this first rectangle and think about it separately, then it is true that the sum of all the other rectangles has to be less than the area underneath that curvature. Right? We can go over here. Right? So we're saying that except for that first rectangle, let's zoom out here. Except for that first rectangle, let's make this first rectangle special, right? Because it extends out to 0 and the integral doesn't work there. Okay, so let's make this first rectangle special. But starting with the rest of them, starting with rectangle number 2, number 3, starting from this point forward, the rectangles are right over here. They can be kind of superimposed onto here, and they go like that. And then the next one is superimposed onto there, and they go on like that, and so on and so forth. So the sum of all of these rectangles that I have in black has to be smaller than the sum of the area in red. The sum of the area in red is this, so it must be true that the first rectangle, let's put it over here. So it must be true that the sum of the first rectangle plus the integral of all this is equal to 2. Good. Now, how do we get that it's equal to 2? Well, we have to find the integral of this. All right, let's find the integral from 1 to infinity of 1 over x squared dx. Right, to find that integral, we're going to have to find the limit as, say, b goes to infinity of the integral from 1 to b of 1 over x squared. Let's just make that x to the negative 2 dx. Okay, so that's going to be equal to the limit as b goes to infinity of negative 1 times x to the negative 1 power, evaluated from 1 to b. Right? Guessing and checking, remember that if I find the derivative of this, bring down the negative 1, that makes it positive, minus 1 brings you there. Okay, so now we evaluate this, the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. Okay, well that's just going to be plus 1. This goes to 0 as b goes to infinity. This heads to 0. So the whole thing equals to positive 1. Okay, so the entire integral from 1 to infinity, the entire area underneath the curvature in red, this whole thing in red equals 1. The area in red, this whole thing equals 1. And I know for sure that the rectangles, starting from this one, which was 1/4, starting from 2, that they are definitely smaller than that. Okay? So the sequence I'm interested in definitely has to be less than the sum of the first rectangle, which is equal to 1 over 1 squared, plus the area in red. Right? So that first rectangle was over here like this, and I put it in like green/red over there. Oh, sorry, green/black from over there. So this is that first rectangle, that guy. And then this function extends out to infinity over this way. So that's why we don't want to mess with it. So we're going to cut it off and think about from 1 to positive infinity, as the domain ranges from 1 to positive infinity. So that first rectangle plus the integral plus that integral from 1 to infinity of 1 over x squared dx, well, that whole thing just equals to 2 exactly. And it must be true that the series we are interested in, the sum as n goes from 1 to infinity of 1 over n squared, well, that must definitely be smaller than this one. Oops, smaller. Must be smaller than this one, right? Because, as we can see from this picture, this integral is definitely larger than the sum of all of these other values. Okay, so if we exclude the first rectangle, the total area of the remaining rectangles is smaller than the area under the curve y equals to 1 over x squared for x being greater than or equal to 1, which is the value of this integral, the integral from 1 to infinity of 1 over x squared dx. This improper integral is convergent and has a value of 1, so the picture shows that all of the partial sums are less than 2, right? Definitely less than 2. That gives us, a cap, right? It gives us a maximum. Thus, the partial sums are bounded, right? Bounded above. We also know that the partial sums are increasing since we keep adding positive terms. Therefore, the partial sums are convergent, right? We know if it's bounded and it's monotone, it's increasing, monotonic sequence, that it's going to converge. And so the series is convergent. The sum of the series, this guy, well, notice that we don't actually have a value for it. I don't know what they're going to add up to, or at least we haven't proven that. But I do know that it's less than 2, for sure. And I know it converges, and it converges to something less than 2. Good. Notice that it was important for us to make sure that each of the terms is positive, because that guarantees that the series is increasing. If the terms were alternating between positive and negative, even if we have an upper bound, we can't guarantee that it's going to converge because maybe it oscillates back and forth, or maybe it's decreasing and there's just a maximum bound, but there might not be a lower bound, or at least we haven't shown it yet. But anyway, it's important to identify that the individual terms were positive, therefore the series was increasing. All we have to do was show that there is a maximum that is bounded above, and those two pieces of information can lead us to conclude that this series is convergent. Good. Okay, let's look at another one that's very similar looking. This one right here. Right, we have the sum of, as n goes from 1 to infinity, of 1 over the square root of n. So here's the first few of them. Square root of 1, square root of 2, square root of 3, 4, 5, so on and so forth. Let's see what this one looks like on Desmos. Well, let's change this to 0.5. That'll do it. There it is. It's that guy. We can also change this to 0.5. Right, that would be the square root. There it is. And these are the individual values on my sequence. 1, 1. Come on. Okay. Here they are. 2, 0.707, 3, 0.5, 577. Okay. So here they are. So now what if we wanted to figure out what this is? Right. So we're going to do the same thing. We're going to find the rectangles. And this time, though, we're going to do something similar, but a little bit different. Okay, so what we want to do this time, remember last time we went to the values of each one of these things, and then we made a rectangle to the left, making it a width of 1, and then that created this rectangle where this base was 1, and the height was the value of the function, which in this case it's 1 over root 1 plus 1 over root 2 plus 1 over root 3, like that. Okay, so this guy is going to be 1 over root 2. And if we go this way, we get this. But that's what we did last time. We just kind of went to the left. And then we showed that the sum of all of these rectangles was less than the area underneath the function, which involved an integral. Okay, but what we want to do this time is do the following. Now we want to take this and go to the right first. The very first rectangle goes to the right and then comes down. Still, we're going to have a base of 1. And now we have left end points. So that's going to be the 1 over root 1 endpoint. And then this one is going to go over here and come down this way and go like that. Good. And this one is going to come down that way and go down this way. Okay, so because this function is decreasing, always positive, like this, it means that if I create rectangles in this fashion, left endpoint rectangles, now the rectangles are always going to go slightly above the blue function. So starting at n equals to 1, right, this is for n equals to 1 right there, I could say that the sum of all of these black rectangles is always going to be a little bit bigger than the area underneath the function, which is specifically going to be looking at this function that goes like that, right? The black rectangles are always going to be just a little bit bigger. Good. So now the area of the red one, well, that's just an integral. That's the integral. This area is equal to the integral from 1 to infinity of 1 over root x dx. And we're going to show that the rectangles, the sum of the rectangles is always just a little bit larger, right, as we can see from our picture. And what's the advantage of this one? Well, we're going to show that if this area diverges, goes to infinity, doesn't converge to some constant, it just grows out of control, well, then these guys must also diverge because they're always a little bit bigger, right? So the way you use this theorem really depends on whether the associated function in real numbers, if it's going to result in an integral that converges or an integral that diverges, right? If it's an integral that converges, you're better off trying to show that there exists a sequence of areas that are definitely below it, and then the integral converges, and you can determine that your series is also going to converge. Or if we have an integral, we have an associated function whose integral diverges, well, then we want to show that our series is going to be a sum of a bunch of areas, a bunch of rectangles that are always a little bit bigger than our integral. And so if this one diverges, goes to infinity, then so must the series itself go to infinity, diverge. Good. So that's what we want to look at. Let's see what your author did over here. Okay, so here is this series. Let's look at a table of values. Again, just using technology. This is the sum of the first 5 values, the sum of the first 10 values, just using technology to crunch them out, right? So just to be clear, this number right here, this is S sub n. This is S sub 5. So that would be equal to 1 over root 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4 plus 1 over root 5. Okay, just calculating all that out using technology, that's what this number is. And then S sub 10, well, that's going to be the same thing, but going out to 10 terms. 1 over root 1 plus 1 over root 2 plus dot, 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 and stopping at 1 over root 10. Right, so using technology, we can see that that equals to this. Okay, so now if we find S sub 50, the sum of the first 50 terms, sum of the first 100, 500,000, 5,000, okay, we can see, we get a sense of what's happening, and it looks like it's just growing out of control, right? It seems to be confirming our suspicions that this series is not going to add up to anything. It just keeps growing and growing and growing. Okay, so here we go again. So we create our function. That's this function here. And now we're going to do left endpoint assignments. So this is 1 over root 1. And instead of going to the left like we did before, we can think about what happens when we go to the right and down. The width is still going to be 1, right? The width of this rectangle is still 1. The width of this rectangle is still 1. All these rectangles have a width of 1. And their height is equal to the value in our sequence, right? So this height right there, that's the height 1 over square root of 2. And this one, that one is the height 1 over the square root of 3. Good. So again, we can convert, or we can rethink about our question, which was 1 over root 1 plus 1 over root 2 plus 1 over root 3 dot, 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 right? So here we're staring at this and we're thinking, okay, this is a sum of weird fractions, but we can convert that and think, no, this is actually a sum of rectangles, okay? They're areas. This is an area question now. Finding this is the same as finding the area of all of these rectangles. Good. They look similar because the way we've created them, the area in this blue is exactly equal to 1 over root 1, right? Because it's 1 times this height. And the area in this rectangle is exactly 1 over root 2. Good? Okay, and what's the advantage of that? Well, now we can compare the area of all of these rectangles in black and compare it to the area of the curvature underneath, right? So let me erase that. So now if we think about the area of the function here, see this area here, it's clear, I hope, that this area in red is always going to be smaller than the sum of all those rectangles. Good. So we have that the series we're interested in, which is this one, this total area is greater than the area of this function for x being greater or equal to 1, which is equal to this integral. Okay, this is the integral. All right, so now what is that integral, right? We want to say that this is definitely larger, whatever that is, it's larger than the integral from 1 to infinity of 1 over root x dx. So let's figure out what that integral is. Let's go over here. That's going to be the integral. Well, let's get rid of this red. The integral from 1 to infinity of 1 over root x dx. Okay, well that's equal to the limit as b goes to infinity of the integral from 1 to b. Then I'm just going to rewrite that as x to the negative 1/2 power, right? The negative sticks it underneath the fraction in the denominator, and the 1/2 is the same thing as taking this square root dx. Okay, and antiderivative to this is going to be equal to x to the positive 1/2 power. And then when we bring that down, we have to multiply by 2, so it's going to be 2 times x to the positive 1/2 power, evaluated from 1 to b, of the limit as b goes to infinity. Okay, so then this is equal to the limit as b goes to infinity of 2 times b to the 1/2 power. You know what, let's just rewrite that as square root of b. Square root of b looks a little neater. Minus 2 times square root of 1. All right, well this is just going to be minus 2. This is the limit as b approaches infinity of 2 root b minus 2. But as b goes toward infinity, square root of a number growing out of control is still going to be a number growing out of control. This goes off to infinity. Minus 2 doesn't make a difference. So the whole thing diverges. right? Gets infinitely large, grows to infinity, diverges. Okay, so this integral, the area underneath the function, diverges. This diverges. And we just established that the one we were interested in is actually even bigger. So if this one is bigger than this one's the smallest of the two, and this one we've established goes to infinity, well then we can conclude that our series also diverges and goes to infinity, even though we don't really know more details of the actual values. Right? On a term-by-term basis, we can always establish that this one has got to be a little bit bigger. Okay, the same sort of geometric reasoning that we used for these two series can be used to prove the following test, the integral test. Suppose f is a continuous, positive, decreasing function on the interval from 1 to positive infinity, and let a of n equal to f of n, right? So in other words, the values in my series, the sequence values, are actually values, individual points on the continuous function f of x. They are arrived. We get the same value by plugging in the nth value into the function f of x, as we do in our sequence. Then the series of a sub n, as n goes from 1 to infinity, is convergent if and only if the improper integral from 1 to infinity of f of x dx is also convergent. In other words, if the integral from 1 to infinity of f of x dx is convergent, then so is the series. The series is convergent. If, on the other hand, the integral from 1 to infinity of f of x dx is divergent, then the integral from 1 to infinity of a sub n is divergent. Okay? Keep in mind that this is only valid as long as f is continuous. We're not doing something weird where we're jumping around. It's a smooth continuous function. It's positive, it's decreasing on the domain from 1 to infinity, and of course there isn't going to be anything weird going on in that domain. Right? Can't have it veer off to infinity or anything. It's decreasing, positive, and it's decreasing on the function domain from 1 to infinity. Then the finding the integral of that function will tell us whether the series converges or diverges. Right? That's what we can get out of this integral test. Here's an example. Okay, so test this series. 1 over n squared plus 1, as n goes from 1 to infinity, test to see if it converges or diverges. We might not know an exact number of what it converges to. We don't have that kind of ability, but we can at least make a decision of whether or not it converges at all. All right, so let's expand this just a little bit to get a sense of what this looks like. This starts from 1 to infinity of this, which becomes n squared plus 1. Okay, so when n equals to 1, we get 1 over 1 squared plus 1, that's 2. Plus, when n equals to 2, we get 1 over 2 squared, which is 4, plus 1 is 5, 1/5. Plus, when n equals to 3, that's 3 squared plus 1 is 5, 1 over 10. Plus, 4 squared plus 1 is 17. Plus, dot, 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 dot. That's what we're interested in, okay? All right, so this is a bunch of ordered pairs in our graph. Let's graph it on Desmos. Okay, so here these individual points represent the series that we're trying to add up. Okay, and then we relate it to, we think about this continuous function, f of x. Right, it's a very subtle distinction, switching it over from an n to an x. But now with an x, we think about the continuous function. And now we want to think about the area underneath the blue curvature from 1 to infinity. We're going to have to try and see if that integrates and if we can conclude with that whether that integral is convergent, if that area exists, or if it diverges. So let's figure that out. Let's go back to this guy. Okay, so we want to compare or think about the continuous function 1 over x squared plus 1. Okay, it's continuous. There aren't going to be anything weird. There isn't going to be anything weird, right? Because there's no way that this can be 0. The only way it can be 0 is if this term is -1, and it can't be negative because I'm squaring it. So there isn't going to be anything weird there. We need to establish that it's decreasing. To establish that it's decreasing, we're going to have to take its derivative. So let's make this f of x equals this function. Okay, so let's take its derivative. F prime of x is equal to the derivative with respect to x of this thing. And I'm just going to rewrite it this way. X squared plus 1 to the -1 power. Right, just rewriting this with the -1. Okay, so this could be the chain rule. This would be equal to -1 times x squared plus 1, -2 power, times the derivative of the inside part, which then equals to -1 times x squared plus 1 to the -2 power, and then the derivative of the inside part becomes 2x plus 0, which is 2x. Okay, so we end up with -2x all over x squared plus 1 squared. That's the derivative, f prime of x. Okay, well, the denominator is always positive, right? Because we're squaring it. Well, because we're squaring this and we're adding 1, that part's always positive. And then we're squaring that, so always positive. And remember that we're only interested in values of x being greater than or equal to 1. So for values of x being greater than or equal to 1, this is always negative. Always negative for this. It can be positive once we start inputting negative values of x, because the negative times a negative equals a positive. But we're only interested in x being greater than or equal to 1. So always negative. Therefore, we've established the derivative is always negative. Therefore, the original function is decreasing. So we've established that. We've shown that f prime of x is negative for x being greater than or equal to 1. So f of x is decreasing on x being greater than or equal to 1. Okay, so it's continuous, it's decreasing. Okay, so now we need to find the integral for this guy. Oh, it's always positive, right? So that's the other thing. F of x is always positive for x being greater than or equal to 1. Good, 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 good. Okay, so now if we find the integral from 1 to infinity of 1 over x squared plus 1 dx. Okay, so then we have to change this, so we can't integrate that, to the limit as, say, b goes to infinity of the integral from 1 to b of 1 over x squared plus 1 dx. Okay, now this can be a tricky integral unless you happen to remember your derivatives of your trig functions. So note that the derivative with respect to x of tan inverse of x is equal to exactly this, 1 over x squared plus 1. Okay, so that's the antiderivative to this thing. No special trick, you just got to remember those derivatives. So this is equal to the limit as b goes to infinity of tan inverse of x as this ranges from 1 to b. And so then this becomes the limit as b goes to infinity of tan inverse of b minus tan inverse of 1. Okay, so now this might be a good time to, again, refresh your memory on the tan inverse function and its graph. So y equals to tangent of x, it's related to that one, means that tan inverse of y equals to x. So roughly, just a really ugly rough sketch here, we would have a graph that looks like this. It kind of comes this way, and it kind of comes that way, and it kind of comes that way. Remember, this is the graph that repeats itself. It'll have vertical asymptotes here, this way, and then this way, and then it repeats itself. It comes over here and goes like that, and repeats itself over here. It comes over here and goes that way. Okay, and then these values there, this is at negative pi over 2, and this is at positive pi over 2. Right, and so this is the y-axis, this is the x-axis, and this is the graph y equals to tan x. That's this graph. Good. Okay, note that one of the points, let's say this point right here, this is pi over 4. Plug in pi over 4, we get 1. And if we plug in negative pi over 4, we get negative 1. Down here, negative 1. Okay, so now we're going to switch around the input-outputs and restrict our domain to just between negative pi over 2 to positive pi over 2 and think about its tangent inverse function. Right, so now if we're graphing x equals to tangent inverse of y, this guy. Okay, what does that graph look like? It'll look like this, and this will come this way and kind of come this way and kind of come this way and kind of come that way. It's this function kind of on its side, where there are asymptotes coming out this way, that and like that, and this is at the line positive pi over 2, and this is negative pi over 2. Good. And then here we had 1 point, pi over 4, 1, so going in reverse, there's a point here 1, which goes there and becomes pi over 4, right? And then there's a point over here, negative 1, comes down here and comes this way and becomes negative pi over 4. Good. Now, okay, so this could be the output is x, to kind of have it the way I have here. This could be that this means that the output is x and the input is y. You know, but these things are just dummy variables, so that might confuse somebody. We can just easily just switch it around to be any other letters. A equals to tan inverse of m. Okay, so the input is an m, and the output is an a. Okay, nothing special about that. But obviously, people really, really like to have x as the input and y as the output. So we can just switch these around and say y equals to tan inverse of x. And then, you know, we're back to a more comfortable setting for our graph, where this is the y and this is the x, right? So it would be more convenient if you constantly think of this as the input, right? Not that there's anything special about the letter x, it's just the input, and this is the output, right? There's some input that goes in there, and there's the output. Okay, so it looks like this, and I know I did a terrible job, so let's see what it would look like with Desmos. Desmos might do a better job. So y equals to tangent x, right? They look like that. So typically we only focus on this one. And there are vertical asymptotes at x equals to pi divided by 2 and pi x equals to pi divided by 2 negative. Okay, let's make these in color and make that red, make that red. Okay, so here is the tangent function, and there's these vertical asymptotes there at negative pi over 2, at positive pi over 2, and then we restrict our domain between negative pi over 2 to positive pi over 2 and just focus on this middle one. Okay, so if we just single out one of the tangent functions, just restrict the domain from negative pi over 2 to positive pi over 2, here's that standard one. And now if we flip this on its side and do the inverse function is going to look like that, where it will have horizontal asymptotes at y equals to pi divided by 2, and y equals to negative pi divided by 2. And let's make those also, let's make them green. And let's make them red. Okay, that's messy. Okay, so if we want to rotate this and find the inverse function of this, it would look like this. Let's take that out, take that out, take that out, and it'll look like this, this. Right, there's the inverse tan function. And notice that this one value here is the result of this, right? The output is, right? There we go. It's right there. Oh well. Okay, and this is the horizontal line y equals to pi over 2, and this horizontal line is negative pi over 2. All right, enough about tan inverse. Back to this guy. So the point is that tan inverse of 1 is going to be pi over 4. And the limit as b goes to infinity of tan inverse, it approaches pi over 2, positive pi over 2, whereas this equals to pi over 4. Right? As the input gets infinitely large, as b in my thing, tan inverse of b, and we have the limit as b goes to infinity. As b gets infinitely large, the function gets infinitely close to pi over 2. Good. And then 1 just leads to exactly pi over 4. So that lets me simplify this to just being pi over 2 minus pi over 4, which then just equals to positive pi over 4. Right? 1/2 minus 1/4 equals 1/4. Okay, so back to our question then. We were originally focused on trying to figure this out, right? So this series is associated with this continuous function. This function we established is continuous. There isn't any vertical asymptotes anywhere. There's no jump discontinuities. There's nothing weird about this function. So it's going to be continuous. We took its derivative. We saw that the derivative is always going to be negative for x being greater than or equal to 1. So we've established this function is decreasing. And it's always positive, right? Any value of 1 gets squared plus 1. The whole thing is always positive. Okay, so all those things have been satisfied. And now when we integrate it, we see that it converges. It converges to pi over 4, in fact. So that means we can conclude that this must also converge. It doesn't necessarily, well, it won't converge to pi over 4, but it will converge, right? We know that this must be, the sum of this must be the sum of this will converge. Starting with the first one kind of gets ignored, but starting with the second one forward, starting with this one forward, we know that the sum of all of those has to be less than or equal to pi over 4. Therefore, 1/2 plus pi over 4 is a maximum for this function. And so it can conclude that it converges. Good. So once again, we have our graph, roughly speaking, kind of does that kind of thing. And we have all these values. So, okay, so if we take that first rectangle and we go like that, we ignore it. This one was 1 over 1 squared plus 1, which is just equal to 1/2. Okay, so that's 1/2. And then we have this other rectangle like that. Okay, so this is starting at 1. So from 1 forward, we were able to find that the integral of this whole thing, this entire area equal to pi over 4. Right? And we were able to establish that this function, f of x, was continuous, it's positive, it's decreasing, so it satisfies all those conditions. And so when we do this one was going to be equal to 1 over 2 squared plus 1. Oops. 2 squared plus 1. So this is equal to 1/5. And then the next one after that, it's this one, 3. That's going to be 3 squared plus 1. That's 1/10. Okay, so we have that 1/2 plus 1/5 plus 1/10 plus ... Right? This is the sequence the series we're interested in. The sum as n goes from 1 to infinity of 1 over n squared plus 1 is equal to this, that way. Good? Whatever this is. So often we say it's S when it converges to S. Converges to S, no subscript. Okay, and so we know that starting with this one, starting with n equals to 2, starting with that one, this right here, this is always smaller. All of these rectangles are always smaller than the area of the integral. Remember, we only integrated from 1 forward, so the area of all this red is pi over 4. So all of this is smaller than pi over 4. So we've established an upper bound. So that means all of these things are smaller than that. So that means that 1/2 plus the pi over 4 has got to be a little bit bigger than S, right? All of this has got to be sort of a roof for S, which is this. So it converges, and it converges to something smaller than this. That's what we can conclude. Good. All right. Let's see what the author did here. Same thing. So the function f of x equals to 1 over x squared plus 1 is continuous, positive, and decreasing on 1 to infinity. So we use the integral test to show that the integral from 1 to infinity of 1 over x squared plus 1 dx is equal to the limit as t goes to infinity of the integral 1 to t of 1 over x squared plus 1, right? And so that one could be a tricky one if you don't remember your derivatives of trig functions. So the derivative of tan inverse is 1 over x squared plus 1. That's something you just got to pull out of your left brain there somewhere, or have a nice table at the ready with the common derivatives. Okay, so we saw that this equals to pi over 4. Hopefully I did a decent enough job of convincing you that that part is true. Thus, the integral from 1 to infinity of 1 over x squared plus 1 dx is convergent, is a convergent integral, and so by the integral test, the series also converges. Good. All right, let's look at something we call the p-series, right? The series, which is the integral of 1 over n to the power of p, is called the p-series, right? Notice that in this case, the p is some constant, right? Once the p is chosen, it stays the same. So this is representative of a whole family of series, right? In other words, this could be the case where we might have 1 over n to the power of 2, right? We've seen that one before. And goes from 1 to infinity. Here, this is where p equals to 2, right? Squared. Okay, all right. Or it could be that instead of a 2, it could be the case where we have n to the power of a third. Here, the p is a third. Okay, so we saw cases where we had a half, and we've seen cases where we had a 2 there. We've worked with cases where we just have a 1, which is just 1 over n, right? So all those family of series are called the p-series family, right? So the p-series, looks like this, is convergent if p is greater than 1, and divergent if p is strictly less than or equal to 1, right? We worked with the case where p was 2, 3, 4, 5, and we've worked with cases where p was equal to a half just earlier here. So this is just confirming the general rule that we have for p-series, the p-series family. Okay, so converges for p greater than 1. So based on this, I could tell that this is going to diverge, right? Because the p is a third. On the other hand, if I had p equal to 7, then automatically by this I can tell that this was going to converge. Okay, p-series. So here's an example. Here we have a case where the p-series equals to 3. The p equals to 3 is greater than 1, so I know it's going to converge, right, based on the p-series. Or here's another one where the p equals to 1/3, right, which is the same thing as the cube root of n. Right, we can expand that out, and I know that this is going to diverge based on the p-series. P is equal to 1/3, that's less than 1, so it's going to diverge. Okay. Determine whether the series ln n over n converges or diverges. Okay, so now back to something more interesting. Okay, so let's just do a couple of these to expand it all out and get a sense of what's happening here. And it looks pretty ugly, right? So n equals to 1 to infinity of ln of n over n. So when n equals to 1, we have ln 1 over 1 plus ln 2 over 2 plus ln 3 over 3 plus ... And ln of 1 we know is 0. 0 over 1 is 0. So I automatically know that this is 0 plus whatever that is. Plus whatever that is. ... Okay, so that's what we're working with. Let's think about, right? So consider the function f of x equals to ln of x over x. And we're only interested, this is for x being strictly greater than or equal to 1. If we think about the graph of ln, the ln graph looks like this, so just a rough sketch of it will look like this, kind of comes this way and goes that way, like that. So it crosses right there at 1. That's why I know that ln of 1 is equal to 0. So for x being greater than or equal to 1, we have positives, right? And, well, for x being greater than 1, this is also positive. So it's easy to conclude that x of x is positive. Whatever that answer is, whatever this is, it's going to be a positive number. ln of 2 is positive, ln of 3 is positive, 3 is positive, 2 is positive. So each one of these values is going to be positive. Positive. Okay, so it's positive. The ln function is continuous, and the function y equals to x is continuous. So a continuous function divided by a continuous function is also going to be continuous. And there is nothing weird about this, this fraction, right? In other words, the only way we can have a vertical asymptote or an undefined is if x equals to 0, but it's not going to be 0 because we're only focusing our attention for x being greater than or equal to 1. So f of x is also continuous, and both of these are on the interval x being strictly greater than 1. Good, for x being strictly greater than 1. I could have put equals 1, because it is continuous at equals to 1. But also if we put a 1 there, then we end up getting a 0. 0 is not technically positive, it's 0. It's 0 is not positive or negative. So that's why I said strictly greater than 1. But we know that at 1 it equals to 0, so it's definitely not negative. And then the last thing we need is to confirm that f of x is decreasing on that same interval. To do that, we're going to have to find the derivative. Okay, so to find the derivative, let's put now, to find the derivative, well, let's put what we want to say is decreasing. And we'll put a question mark here because we haven't proved that yet. Question mark. Okay, so is it decreasing? To figure out that it's decreasing, I need to find the derivative, f prime of x. Okay, f prime of x, well, that's going to be d dx of my function, which is equal to ln of x over x. Okay, well, that can be a quotient rule, low d high minus high d low over the denominator squared we go. Okay, low d high minus high d low over the denominator squared we go. No, sorry for my singing. The derivative of ln x, that's just going to be equal to 1 over x. Right, we know that simple derivative. And the derivative of x, well, that's just going to be 1. And then we end up with x times 1 over x minus ln of x times 1 all over x squared. And then x times 1 over x, these guys cancel. And so we end up with f prime of x, the derivative of the function, is equal to 1 minus ln of x all over x squared. Okay, well, this denominator is always positive because we're squaring it. Always positive. And then this guy, remember that we're only interested for x being greater than 1. And again, remembering our graph for ln x. Remember our kind of a rough sketch here looks like that. 1 is right there. Okay, so 1 leads to 0. So we need to figure out when this is going to be negative. So 1, let's put it over here. We want to figure out when is this negative. So 1 minus ln x is going to be negative. It's going to be less than 0 for what values of x, right? So that means that 1 is greater than ln x, which means e to the 1 is less than e to the ln x, or e is less than x. So x has to be greater than e. That's what this is saying. So if we go out here and we figure out the input value of e, right, this is ln of x, and we think about where the input value of e is, ln of e is just going to be equal to 1. And for x values that are to the right of that, whenever it's bigger than that, then the output of the ln function is going to be bigger than 1. Therefore, 1 minus this result will be negative. Good? So that's what we can conclude here. It means that this thing is always negative. Always negative for x being strictly greater than some constant e. Okay? And that's okay. We don't need, we need to know what happens as we go toward infinity. So maybe it doesn't, the function, maybe the original function f of x doesn't begin life decreasing the entire way. Maybe it increases, maybe it hits some max and then starts coming down, or maybe it's flat and then starts coming down. But we've established that starting at e, moving forward, it begins to decrease. Good. Let's see what this graph looks like. Oh, and so that means, just to kind of finish off this thought, taking the derivative and showing the derivative is negative starting at e forward, we've established this part right here. The original function is decreasing. Right, so now this is no longer a question mark. Now we've shown that yes, it's decreasing. F of x is decreasing because its derivative is negative for x being greater than e. Okay, so let's graph it and see what it looks like. Let's go back to Desmos. Good old Desmos. Okay, so ln x divided by x looks like this. And look, it begins over here, life increasing, and at some point it kind of reaches some maximum value, and that one point is going to be found at e. So let's figure out what that value is using here. Let's graph the point e, comma, f of e. Make sure there's no other f's. F of e. Like that. So this function was increasing up to there, and then it begins to decrease, and it'll decrease forever. Okay? All right, so now back to this guy. Okay, we've established that the function f of x is positive, continuous, it's decreasing. Now we need to know, well, what is the integral of that function? Does it converge or does it diverge? Right, so now let's find the integral from 1 to infinity of ln x over x dx, which is equal to the limit as b goes to infinity of the integral from 1 to b of ln x over x dx. We can easily figure this out by doing a u substitution. Let's let u equal to ln of x. Its derivative, du dx, is going to be equal to 1 over x. du is going to be equal to 1 over x dx. Okay, and so now let's replace this guy over here. This is going to be equal to the limit. Well, let's put it below actually. This is going to be equal to the limit as b goes to infinity of the integral. Now I deducted a little bit before on the test, so this is what I meant if you weren't quite sure why I deducted some points on your test. By default, if you don't put anything on these limits of integration, it's assumed that these limits refer to the same variable there, that this is x goes from 1 to x equals b. It's an assumption that I think often leads to some weird, problems people have. So when I make my u substitution here, okay, I'm going to let u equal to ln x, that's this thing, and luckily 1 over x dx, that's right there as well. Right? This is just kind of breaking this up. this is equal to the limit as b goes to infinity of 1 to b of ln of x times 1 over x dx. Good. And again, by default, it's assumed that these limits here match the same variable. When I do my u substitution, I have the choice to either figure this out again with the new values, putting in each one of these, so I can find my new value of u, so that I can figure out what this is, u equal to there and u equal to there, and I'm going to have my new du. Or you can leave them alone. I'm okay with that. That's very common. Just make sure you leave the fact that this is an x, just so that it's clear to everyone that you haven't changed the variable in the limits of integration here. Okay? All right, so now if we're changing it to u, that means that this is going to be my u, and this entire thing is my du. Okay, so that's just going to be u times du. Luckily, that is a fantastically easy integral to solve. So this will be equal to the limit as b goes to infinity of 1/2 u squared, right? The antiderivative of u squared is going to be equal to 1/2 u squared, evaluated as x goes from 1, x goes to b. And now what I'm going to do is come back over here and replace what u was. U was equal to ln of x. So now I'm going to say that this is equal to the limit as b goes to infinity of ln of x squared divided by 2. That's just replacing that u with ln of x, evaluated as x goes from 1, x goes to b. Okay, so this is equal to the limit as b goes to infinity of ln b squared over 2 minus ln 1 over 2. But ln 1 was exactly equal to 0, so that's just 0. And as b goes to infinity, ln of b is going to go to infinity. Squaring it just makes it go to infinity that much faster. And dividing it by 2 will slow it down, but not enough for it to make a difference. This is still going to go toward infinity. It diverges. Okay, so we've established that the continuous function diverges. So that means we can conclude that our series is also going to diverge. Let's put all that together. Okay, so putting it all together, we were working with this guy. We wanted to know what happens to this series. Is it going to converge? Is it going to diverge? What's going to do? Okay, we compared it to our continuous function, ln x over x. We found that this function is positive, continuous, and decreasing for x being greater than e. Okay, and then we've just discovered that the integral of all of this, the integral from 1 to infinity of ln x over x diverges. So we can conclude that this guy is also going to diverge. Let's see what your author did for this guy. Hopefully something similar. Solution, f of x equals to ln x over x is positive and continuous for x being greater than 1 because the logarithmic function is continuous, but it is not obvious whether the function f is decreasing, so we compute its derivative. Okay, so here's the derivative. low d high minus high d low. We end up with this. Good. The derivative is less than 0, in other words, negative, when ln x is greater than 1, that is, when x is greater than e. It follows that f is decreasing on x is greater than e, and so we can apply the integral test. Okay, so then we figured out this integral, and we end up with the same conclusion. It goes off to infinity. It diverges. Since the improper integral is divergent, the series is also divergent by the integral test. Good, 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 good. Okay, estimating the sum of the series. Estimating the sum of the series. Suppose that we have been able to use the integral test to show that the series a sub n is convergent, and we now want to find an approximation to the sum s of the series. Of course, any partial sum s sub n is an approximation to s, because the limit as n goes to infinity of s sub n equals to s. But how good is such an approximation? To find out, we need to estimate the size of the remainder, the part that's left over, right? And that would be r sub n, the remainder, where r sub n is equal to s minus s sub n. So remember that s sub n is the sum of the first n values of our sequence. And so if we take the total sum minus the first n values in our sequence, well, that'll be the remaining values, right? So, in other words, s is, since it converges to s. S is exactly equal to a sub 1 plus a sub 2 plus a sub 3 plus ... Now over here we'll end up with a sub n minus 1 plus a sub n plus a sub n plus 1 plus a sub n plus 2 plus ... forever, right? Okay, so the sum of the first n values, right, stopping at n, that's s sub n. So if we take s minus s sub n, right, we take all of these and subtract them onto the other side of the equal sign, we'll be left with this part right here, which will be a sub n plus 1 plus a sub n plus 2 plus ... Okay? Good. Okay, and that's what we call the remainder, r sub n. Okay, we use this same notation and ideas as the integral test, assuming that f is decreasing on from n to infinity, and comparing the areas of the rectangles with the area of the function y equals to f of x for x being greater than n. And in the figure we see the following. Okay, so this image, let's zoom in on it, is showing that if we go, here's n, if we go to n plus 1, here's n plus 1 right over here, and we go to the left, we create, here's the result of plugging in n plus 1, right? So this is a sub n plus 1 here, and this one is going to be a sub n plus 2 over there. Okay, so if we go to the left, then all of these rectangles in blue are definitely going to be smaller than the area underneath the function starting at n, right? Starting here, that area is going to be this. And so the r sub n, the sum of a sub n plus 1 plus a sub n plus 2, so on and so forth, is definitely going to be smaller than that integral. On the other hand, if we jump over and start at n plus 1 and go to the right and come down, and then go to the right and come down, so this height right here would be the a sub n plus 1 value, right there. And then over here, this one would be the a sub n plus 2 value, right over there, and so on and so forth. Looking at it from this perspective, we see that the sum of these rectangles is always going to be a little bit larger then the area underneath the function, which is this one right here, so the area underneath the function starting at n plus 1. N plus 1 is going to result in an area underneath the curvature of the function f of x, which gives you an area that's a little bit smaller than the r sub n value we're looking for. And then over here on this case, the area underneath the function f of x is going to be a little bit larger than the sum of the rectangles that we're looking for. So this is going to represent an upper bound, whereas this is going to represent a lower bound, right? And the only thing that's different is this guy, whether you're going to integrate starting at n plus 1 or integrate starting at n. Okay, so we have proved the following error estimate. Suppose f of k minus a sub k, where f is a continuous function. Okay, so I think this is equals. Suppose f of k equals to a sub k, where f is a continuous positive decreasing function for x being greater than or equal to n at least. Okay, and we already know that the series is going to be convergent. Okay, so we've already established that. If the remainder r sub n equals to s minus s sub n, then we know that that remainder is trapped between these two things. It is the integral, the lower bound is this one, the integral of f of x starting at n plus 1 to infinity. This is a lower bound for that remainder, whereas the integral starting with n to infinity becomes an upper bound. So that remainder is less than that. Okay, all right, let's look at an example. Approximate the sum of the series 1 over n cubed by using the sum of the first 10 terms. Estimate the error involved in this approximation. Okay, so this is part A. Is just going to ask us to figure out what this is. S sub 10. Find the sum of the first 10 values. So that'll be 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed plus 1 over 5 cubed plus 1 over 6 cubed plus 1 over 7 cubed plus 1 over 8 cubed plus 1 over 9 cubed plus 1 over 10 cubed. Okay, so you're welcome to actually add these up. You can get your calculator and add them up one at a time. You can simplify it if you want to by finding these cubes and then adding each one of those. Or, you know, we can take a little bit of a shortcut using our calculator still. So let me do it this way. I'm going to go over here. I'm going to hit Stat. I'm going to hit Edit. I'm going to clear list 1. So I'm going to go to the left, up, and then where it says L1, hit Clear, Enter. And then L2, make sure you use your arrows to get up to where it says L2, hit Clear, Enter. Go to the right, go up there, hit Clear, Enter. If you're thinking, man, my calculator doesn't even have these L1s, L2s, then hit Stat, go down to where it says Setup Editor, hit Enter, done. That'll fix it. I mean, somebody had previously deleted it. So you're going to hit Stat. That takes you to this menu. You're going to hit Enter. And then L1, L2, L3, I'll use those. So I'm going to put the values of n onto list 1. So I'll put 1, Enter, 2, Enter, 3, Enter, 4, Enter, 5, Enter, 6, Enter, 7, Enter, 8, Enter, 9, Enter, and 10. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so now next, over here, I want to put in the values of each of these. So 1 over 1 cubed, 1 over 2 cubed, 1 over 3 cubed. That's what I want to put here. And to do that, I'm going to do column operations. I'm going to use my arrows to go up to where it says L2. And now I can do arithmetic with the other L's. So for example, if I just did L1 plus 5, it's going to go term by term here and add 5 to every one of those values. Hit enter. See, 1, we add 5, we add 5, we add 5, we add 5. Okay, but we don't want to add 5. What we want to do, clear, is we want to do 1 divided by L1, all the values in L1, to the power of 3. Close parentheses, go to the right, close parentheses, like that. Hit enter and confirm that things look good. So the first one is 1, that looks good. And then the next one, that's going to be 1 over 9. And then the next one after that, I'm sorry, 1 over 8. This one's 1 over 8, 2 to the third power. This one's going to be 1 over 27. Okay, and then 1 over 64, and so on and so forth. So that's all those values. And then if I want to find the sum of all of those, then I'm going to do stat calculate one variable statistic on list 2. And this gives you a whole lot of stuff about that list, including the sum of the numbers in that list. So this gives you a lot of stuff we don't need in this class, but right here, this is what we want. The sum of X values, the sum of all the values on that list. Notice that when I did it, okay, let me do it again. Stat, calculate, one variable statistics, hit enter. And now I chose L2 because that's the list that contains all the values I want to do, okay, that I wanted to add. So calculate, and then there it is. So the sum of those values adds up to 1.1975, 1975. So S sub 10 adds up to 1.1975. Okay, so now next it's asking us to estimate the error involved in this approximation. We got an approximation, but now let's have some estimation about the error. Okay, so that means that we need to figure out some value for R of 10. Okay, so from before we saw that R of 10 is definitely less than the integral from n to infinity of our function, which is going to be equal to 1 over x cubed dx, where this n is equal to 10. N equals to 10 in our case. Okay, so let me figure out what this is over here in general, and then we'll be able to use it. So leaving it as a n, let's figure out what this is over here. So let's figure out the integral of n to infinity over 1 n x to the power of 3 dx. Okay, well that's just equal to the limit as b goes to infinity of the integral from n to b, and I'm just going to rewrite this as x to the negative 3 power dx. Okay, that one's fairly easy. The antiderivative is going to be something involving a negative 2, and so we bring that out in front. That's going to be a minus 2 minus 1, so minus 2 is going to be negative 1/2 out here. The limit as b goes to infinity of this, evaluated from n to b, good, which then equals to the limit as b goes to infinity of negative b squared all over, well no, negative 2. Negative 1 over 2 b squared minus a negative, so plus 1 over 2 n squared And the limit as b goes to infinity of this term, it's going to go to 0. And then b is not a term here, so it doesn't affect it. So the whole thing is just going to go toward 1 over 2n squared. Good? That's what this is. All right, so 1 over 2n squared. 1 over 2n squared. Well, that means that coming over here, this is going to be equal to 1 over 2n squared. Where n is actually equal to 10, right? So let's just erase this guy here. For us, this is a 10. Okay, so this is equal to 1 over 200. 1 over 200, well, that's equal to, let's quit here, clear 1 divided by 200 equals to 0.005. 0.005. Okay, so the error is less than 0.020 in the 5. 0.005. Good. Okay, so that's the answer to part A. Part B, how many terms are required to ensure that the sum is accurate to within 0.0005, right? So we were accurate to 0.005 when we added the first 10, but what if we wanted to be even more accurate, even closer to an answer, to be within this much? Okay, so I want to kind of reverse engineer this to figure out the value of n, and I'm going to work with this right here. This we know was 1 over 2n squared was the result of finding this integral from n to infinity of 1 over x cubed dx. And we knew that this was going to represent sort of an upper bound for that r value. So let's say that we're looking for k, r sub k, and we need to figure out what that k value is going to be such that this remainder over here is equal to 0.0005, another 0 in there. Okay, so that means that this is going to be kind of matching there, so that means that this is when this equals to k, from k to infinity, and I want this whole thing to give me that, which means that I need to plug in a k there. It's going to be this. It's going to be the k value there, such that the integral from n equals to k to infinity of this, which we know equals to this formula, 1 over 2 times k squared. I want that to be equal to this, so now we just have to figure out what k is based on this. Okay, so just a little bit of algebra now. 1 over 2k squared, I want that to be equal to 0.0005. So multiplying both sides, we get that 1 equals to 2k squared times 0.1235. So multiplying those two together, we get that 1 equals to 2. 2 times 0.005, which equals to k squared times 0.001. So 1 divided by 0.001 must be equal to k squared. 1 divided by 0.001 is equal to 1,000 equals to k squared. So we take the square root of it, square root of 1,000 equals to k. And so we get let's confirm some of my arithmetic here. 0.123 times 5 times 2 gets me to 0.001, and then 1 divided by 0.001 gets me to 1,000, and now the square root of 1,000, equals 31.6228. 6228. Of course, we can't let k be a decimal value. K represents an integer value, right? It's a location on the list on my sequence. And so we just have to bump this up to the nearest one. So we must let k be equal to 32. K equal to 32. So if we want to be within 0.0005 or smaller, then we need to figure out S sub 32. The sum of the first 32 values will be within 0.0005 of the actual value S, right? That's what this means. Let's go down here. Let's see what the author did. Okay, the integral from n to infinity of 1 over x cubed dx equals to the limit as t goes to infinity of 1 over 2x squared. Okay, same thing as me. Okay, so we end up with this. Approximating the first 10 values. Okay, that's hopefully what we got, 0.1975. R sub n must be less than this, which we got 1 over 200 equals to 0.05. Accuracy to within 0.0005 means that we have to find a value of n such that this is true, and it's less than or strictly less than 0.005. Okay, good. So we end up with the same thing. So we need the first 32 terms. If we sum up the first 32 terms, that summation will give us a value that is within 0.0005 of the real value of S. Good, good, good. Okay, final thing in this section, estimating the sum of a series. So if we add S sub n to each side of the inequalities up in number 2, we get that this is true, right? In other words, we have this inequality that let's see, let me refresh your memory on some of this notation. S sub n, so we had S is equal to A1 plus A2 plus dot, 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 plus A sub n minus 1 plus A sub n plus A sub n plus 1 plus A sub n plus 2, and then this goes on forever, right? Dot, 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 dot. Okay, so the sum of the first n of them, that's these, that's S sub n. And then the rest of them, the remainder, that's these guys over here, this is R sub n. So if we subtract them, we end up with S minus S sub n. That's going to be equal to the R sub n value, right? That's the notation we have. Okay, so in other words, if we add S sub n to both sides, right, S sub n plus R sub n, it equals to S. S equals to S sub n plus R sub n. If we can add those two things together, we'll get the actual value of S. So we established that there is a inequality. There is an we established that there is an inequality that can help us trap R sub n. R sub n is definitely smaller than n to infinity of f of x dx. But that there is a lower boundary to this that starts at n plus 1 to infinity of f of x dx. So if we add s sub n to all three parts of this inequality, s sub n plus that, s sub n plus that, s sub n plus that, then this becomes the actual value of s, and so s is strictly less than s sub n plus the integral from n to infinity of f of x dx, and strictly greater than s sub n plus the integral from n plus 1 to infinity of f of x dx. Good. And this looks a lot like an integral here. So this is s, not an integral, so s. And so we have this inequality here. Right, that's the inequality that we have over here. S sub n plus the integral from n plus 1 to infinity of f of x dx is less than or equal to s, less than or equal to s sub n plus the integral from n to infinity of f of x dx. Good. So this three-part interval where we can definitely say that s must be inside that interval. Right? It establishes a lower bound and upper bound for s. They provide a more accurate approximation to the sum of the series than just the partial sum of s sub n. Okay, so now let's take a look at some of the homework problems. Section 11.6. Okay, let's see, 3 through 8. Use the integral test to determine whether the series is convergent or divergent. Let's do number 8. Okay, so determine whether this is divergent or convergent by the integral test. Okay, so number 8 has n squared e to the negative. Okay, so in order to be able to answer this question, we want to think about the continuous function. Think about the function f of x equals to x squared e to the negative x cubed. Okay, so this can also be rewritten as f of x equals to x squared all over e to the x cubed function. Okay, so x cubed is continuous, e to the x cubed function has to be continuous, right? So this is a composition of functions where we could have e to the power of, could be x, could be w, doesn't matter, right? So this is the input. So this is a continuous function. Let's call it w in there. So this is a continuous function, f of w. And then we have a cube function here. So we could call that g of, I don't know, p equals p to the cubed, right? The letters themselves don't matter, right? We have some input getting cubed, right? So whether it's an x or a p doesn't matter. And then here we have e to the power of some input, right? Whether it's a w or an x, doesn't matter. So we have a composition of functions here, and this one is a continuous function. This one's a continuous function. There's nothing weird going on in terms of to the power of 0, negative exponents, nothing unusual. And we're only interested for x being greater than or equal to 1. So that in particular, we're not going to have anything unusual. This is always going to be positive. E to the power of, this is always going to be positive. so that looks good. And then x squared, of course, is continuous. Okay, so without really proving it, I think it's easy to convince you that f of x equal to x squared times e to the negative x cubed is continuous. Right? This is good enough for our purposes. On x greater than or equal to 1, right? That's all we really care about. Next, positive. Is this always positive? Well, going back to this again, x cubed is always going to be positive. E to the power of something that's always positive is also positive. And x squared is positive, so the whole thing is always positive, right? So f of x, I know, is positive for x greater than or equal to 1. And finally, we need to determine whether this function is decreasing. That one is the one that's a little tougher. To show that the function is decreasing, we're going to find its derivative. So we're going to find f prime of x, which is equal to d dx of x squared over e to the x to the power of 3, right? So we're going to have a quotient rule situation. So low d high minus high d low over the denominator, squared we go. Over the denominator, squared we go. Okay, so that looks fairly ugly. So let's simplify that just a little bit. That means that the derivative of this guy, that's easy, that's just going to be equal to 2x. And the derivative of this thing, okay, so the derivative of e to the power of x cubed, that's just going to be equal to e to the x cubed times the derivative of the exponent, right, the chain rule, d dx of x cubed, and then that in itself equals to 3x squared. So let's write that all down. This is going to be equal to e to the x to the power of 3 times 2x minus x squared times 3 times x squared e to the power of x to the power of 3. All of that gets divided by e to the x cubed, and the whole thing is being squared. Okay, so now we can further simplify this a little bit. These two are like terms, so we can combine them. And we can factor out a power of e to the x cubed from the numerator. E to the x cubed remains is 2x. These two combine to give me a e to the x cubed squared. Okay, so then one of these cancels with one of these. Cancel out this guy with one of those. And in fact, well, I guess I could have factored out an extra x out of there. I don't know why I didn't do that. So this is equal to x and then 2 minus 3x cubed all over e to the x cubed. Okay, remember this is only for x being greater than or equal to 1. Right? So for x being greater than or equal to 1, this is always positive. Any number that's positive being cubed is going to be positive. And then e to the power of any value really is positive. This is always positive. Right? So always positive. Now the numerator here, this guy is going to always be negative past a certain point. So x is always positive, so this guy is always positive, right, for x being greater than 1. So now the question is when is this negative, right? This is negative sometimes. So when is it negative? So let's take that off to the side and think about what that says. So this is going to be negative. The whole thing is going to be negative whenever 2 minus 3x cubed is negative, below 0, which means 2 is less than 3x cubed, which means that 2/3 is less than x cubed, which means we're looking for the cube root of 2/3. And, well, that's going to qualify for x greater than 1, right? Remember, we're only really interested in what happens as x goes out to infinity, and so it all gets satisfied, right? I mean, we can get the actual value. 2/3 the power of 1/3. 2 clear. 2 divided by 3, and then raise that to the power of 1/3. 1 divided by 3. And we get 0.8736. 8736. 0.8736. So as long as x is greater than this decimal, everything is fine. We're going to be negative, right? So 1 qualifies, and that should make sense here. 1 cubed is 1, which makes it 3, and 2 minus 3 is negative 1, so already it's negative at that point. And as x gets larger and larger and larger, we're only going to further cement this as a really big negative. And then times a positive stays negative, divided by another positive stays negative. Okay, so we've established that the derivative, let me zoom out a little bit here. What we've established is that the derivative of this thing is negative, right? The derivative of this is then going to be equal to this. F of x equals this. F prime of x equals that, which means f prime of x equals this. And we've established that indeed f prime of x is negative. It's less than 0 on this domain. Okay, so now we've got the trifecta. We know that it is positive, we know that it is decreasing, and we know that it's continuous. So now we can apply the rule. Okay, so let's find the integral. Hopefully that part's easy. Okay, so back to this guy. We want to find the integral from 1 to infinity of x squared e to the negative x cubed dx. Okay, so to find that integral, we're going to say that that's actually equal to the limit as b goes to infinity of the integral from 1 to infinity, from 1 to b, of x squared times e to the negative x cubed dx. Okay, and so to solve this one, let's do a little u substitution. Let's let u, let's put it in blue, let u equal to the negative x cubed. Therefore, du dx equals to negative 3x squared, which means that du equals to negative 3x squared dx. And so we're really close, right? We're almost there. So let's repeat that over here. So this is equal to the limit as b goes to infinity of the integral from 1 to b of this thing. We have e to the negative x cubed, and then there's an x squared dx. And then I'm just going to introduce the thing I need. I need this to be a negative 3. That way I have exactly my du. This one is now my du. But then I got to balance it out with a negative 1/3 out here. That way this times this equals to positive 1. Okay, and so now I can do my substitution and say that this is equal to the limit as b goes to infinity of the integral. Oh, there's a negative 1/3 out here, negative 1/3. And this, okay, so allow to be perfectly direct with this. This is x goes from 1, x goes to b. So I'm going to keep those guys. I'm going to put them there because now I'm going to change my limits of integration. Right? So this becomes e to the power of u, e to the u, du, because this is exactly my du, and this is my u. Oh, this guy's my u, including the minus sign. Okay, so now I can integrate this. Very easy guy to integrate. The limit as b goes to infinity. And then I have this negative 1/3 and that's e to the power of u. It's just the antiderivative of e to the power of u is just e to the u. Evaluated as x changes from 1, x goes to b. And now I can go back and replace my u. And my u was actually negative x cubed. So this becomes the limit as b goes to infinity, negative 1/3 e to the negative x to the power of 3, evaluated as x goes from 1 to x goes to b. So this is equal to, let's factor out that constant out here, negative 1/3 times, and then I'll have the limit as b goes to infinity of e to the negative b cubed minus e to the negative 1 cubed. Okay, so 1 cubed is 1, e to the negative 1. And here we have b is growing, b cubed becomes even bigger. And so we have e to the negative, a really big negative number. And if we think about our graph for e, it's like a really rough sketch for what the graph of e looks like. E looks like this. Is the function e to the x power. So as x goes toward negative infinity, this whole function grows towards 0. So that's what's going to happen to this. This whole thing grows towards 0. Good. Okay. So then what we end up with is negative 1/3 times something that grows to 0 minus e to the something that grows toward negative 1. Well, it is negative 1. So this then becomes negative times a negative becomes a positive. So this becomes positive 1/3e. That's what it converges to. Okay, so the actual value it converges to is almost not really important. It matters that it does converge. So we've established that this this function back up here, we've established that this function, after all this work, we've established that this one converges to 1/3e. Okay, so because this continuous function, because this function is continuous, it's decreasing, it's positive, and it converges to this number, now we can conclude that this series that starts from 1 to infinity on n squared e to the negative n cubed also converges. Good. It doesn't necessarily converge to that, but it does converge. All right, let's see what else we got. Let's go back to, okay, that one's number 8. Let's look at something over here in the low teens. Determine whether the series is convergent or divergent. Remember the P series, family of series. And we know that they converge or diverge based on the power p. So let's look at something like number 14, for example. Figure out if this converges or diverges. A nice, straightforward little pattern like this one. So this is chapter 11, section 3, number 14. Okay, so we got 1 plus 1 over 2 square root of 2 plus 1 over 3 root 3 plus 1 over 4 root 4 plus 1 over 5 root 5 plus dot 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 dot. Okay, we get the point after that. It's a pretty straightforward little pattern. So does it converge? Does it diverge? Let's take a look at it. Okay, so the first thing I would do is to recognize that this whole thing, this pattern, can be rewritten in this style of notation as 1 over n root n, as n goes from 1 to infinity. Right, let's just confirm it. When n equals to 1, we get 1 root 1, which is just going to be a 1. Okay, that explains that first one there. And then when n equals to 2, we get 1 over 2 root 2, then 3 root 3, then 4 root 4. Okay, so this one is it. And now this guy can be rewritten this way. This is the same as the Riemann sum from 1 to infinity of 1 over n times n to the 1/2 power. And then also we can put a 1 there. They have the same denominator, so what we have to do is add the exponents. So this can be rewritten as the sum from 1 to infinity of 1 over n to the 3 over 2 power, right? Adding those two together. And now this follows the family of the p-series family, right? So we saw somewhere in our notes that the Riemann sum of 1 over n to the power of p as n goes from 1 to infinity, that this converges for p being greater than 1, right? So this fits that form. Here, the p, which is equal to 3 over 2, is greater than 1, so it converges. So, converges. Okay, let's move on. How about something like number 20? What should we do here? Number 20. So this is chapter 11, section 3, number 20. We have the sum as n goes from 3 to infinity of 3n minus 4 divided by n squared minus 2n. Okay, number 20, what do we do with this guy? So, well, first of all, we're interested in this continuous function, right? So we want to consider f of x equal to 3x minus 4 divided by x squared minus 2x. Okay, why don't we try breaking this up and seeing if we can rewrite this as the sum of two separate fractions, do partial fraction decomposition on this guy, and simplify it that way. So we have 3x minus 4 over x squared minus 2x equals to blank. Well, no, we have to we have to factor out the denominator. So that'll be x times x minus 2, and then that'll be 3x minus 4. Okay, it qualifies, right? Noting that this is degree 1 and this is degree 2. So it's a proper polynomial fraction. And And so, by the rules of partial fraction decomposition, I know I can find a fraction where the x in the denominator plus another fraction with the x minus 2 in the denominator. And I know that there's going to be a couple of constants I have to determine. Constant there and some constant there. Okay, so I'm just going to copy this over here. This is 3x minus 4 divided by x times x minus 2 equals to x plus x minus 2. And if you're wondering, well, where did I get the idea to do this? It's just practice. You know, first time you do these things, it doesn't occur to you to do that. It doesn't occur to me to do that. The first time I saw these, I didn't know what to do with it, but I've seen these quite a bit, and so I'm kind of thinking this might work. It might not work. If it doesn't work, then I'll come back and try something else. Okay, so we are going to multiply this by this, and this by this. Right, so all of it. That way I'm doing the same operation of both sides of the equal sign. And now I'm going to distribute this to both fractions. And on the left-hand side, everything cancels. Noting, of course, that x is not allowed to be 0 or 2, because then we'd end up dividing by 0 here, right? So we're going to let's make sure to point that out. X is not allowed to be a 0 or a 2. Okay. And then we end up with 3x minus 4 is equal to capital A times, okay, one of the x's canceled. I'm left with an x minus 2 plus a bx. Good. All right, so multiplying these guys, we end up with ax minus 2 times a plus bx. Good. Combining those two minus 2a, we end up with 3x minus 4 equals to a plus b times x minus 2a, right? And then comparing it to the values on the left, right? This is the constant and this is the constant. So it must be true that the capital A must be a positive 2 in order to match up that one, right? So we can just conclude A must be 2. 2 times 2 is 4, and that matches with that constant. Okay, so now we have that the 3 must be equal to the A plus B. So we get that 3 must be equal to A plus B, and the A is a 2. So it must be true that the b equals to 1. B equals 1. Okay, so now we have our constants. The a equals 2, the b equals to 1. Right, so coming back up here, I can say that this is equal to 2, and this guy equals 1. Okay, so bringing it together after the partial fraction decomposition, I can say that this function I was thinking about is equivalent to 2 over x plus 1 over x minus 2. Okay. All right. Now this is two separate functions, summation of two functions. Now each function is clearly positive for x greater than 1, positive for x greater than 1. Clearly each function is decreasing for x greater than 1, right? This is an easy one to tell. If not, you can just take its derivative, right? If we take the derivative of 2 over x and we want to take its derivative, the derivative of this guy is just going to be equal to negative 2 over x squared, which means it's always negative, right? Always negative. Same thing with this one when we take its derivative. So it's decreasing, it's positive, it's continuous. Okay, so what we can do is we can integrate each one of these, and if we can show that the integrals converge or diverge. That'll give us an answer for what we're looking for. Good. Okay, so all the setup, all the stuff we need to consider has been. Okay, so now let's go back over here and figure out the integral we need. This is going to be the integral, and noting that we're interested as n goes from 3 to infinity, which coincidentally helps us out because over here we saw that we have a problem when we input a 2. So if we tried to integrate from 1 to infinity, as we normally do, normally these things start at 1, if we do that, we're going to end up with a problem when n equals to 2, since then that becomes 0, right? Which becomes a problem over here as well. That's 2 squared is 4 minus 4, that's becomes 0. Okay, but luckily this has a 3 there, so we don't have to worry about that. So this is the integral from 3 to infinity of 3x minus 4 divided by x squared minus 2x. Okay, so to deal with this guy, we're going to have to tweak this a little bit. This is equal to the limit as b goes to infinity of the integral from 3 to b of, and then this guy, well, we already know that it equals this. So we're going to separate this into 2 over x plus 1 over x minus 2 dx. Good. Okay, so we can separate each one of these integrals. This is then equal to the limit as b goes to infinity of the integral from 3 to b of, well, we can separate into 3. No, never mind, I don't want to do that. This is pretty straightforward at this point, right? So let's just go ahead and figure out its antiderivative. Its antiderivative of this is just going to be ln. So this is 2 ln x. Remember, the derivative of ln is 1 over x, so that equals this, plus ln of x minus 2, evaluated from 3 to b. Okay, so plugging in b's and then plugging in 3's, we end up with the limit as b goes to infinity of 2 ln of b plus ln of b minus 2 minus ln of 3, 2 ln of 3, minus ln of 3 minus 2. Good. 3 minus 2, that's just going to be 1. This whole thing is ln 1. And ln 1 is 0, so this whole thing just becomes 0. Okay, this is some constant. 2 minus 2 ln 3 is just some constant value. And note what happens here. Remember, the graph for ln looks roughly like this. The rough sketch of it looks like this. ln x, y, x. Good. And so as x goes toward infinity, a function grows. So this is just going to go out to infinity. This grows to infinity. Plus, well, this thing is also just growing out of control. That's also going to infinity. Luckily, they're both pluses and they're adding to each other, right? We'd have to do some more work if they were subtracting from each other, right? Which infinity wins? Do they cancel out? They're both adding. They're both growing. So together, they're both going toward infinity. And this is just some constant slowing it down, minus this. But it will make a difference. The whole thing grows toward infinity. The whole thing is divergent. Okay, so because the integral is divergent, then finally we can go back to our original question and conclude that it must be the case that our series is also divergent. Okay, so I think that should give you enough material to get started on the homework and hopefully get through the homework. So that's a good place to stop.